So stream ciphers are one family of ciphers. So if you understand them, we only covering 2 examples, but all other stream ciphers will have similar features, similar way the way they work. That's why when we study these crypto systems, we study their families and we take examples of each family. And when you encounter other ciphers, as soon as you know which family, you already have an idea how this particular cipher works. So that's why this categorization of categories of crypto systems is very helpful, because you cannot cover all the ciphers out there. There are so many of them. So now here is the kind of, now I cracked the perfect outline of this session. Is the idea is, first it started with the one-time pad. It's the idea of stream cipher started with one-time pad. And as we discussed, the one-time pad, the idea of it, you have a key the same size as the plain text, and that key you use it only once. This is perfect, unbreakable, unconditional security. You cannot break it even if you have all the computer resources of the world. But it has the inconvenience of having a large key. You have to maintain that key and exchange that key. So that's why it is impractical. It is very secure, but impractical. So the stream ciphers came along as a solution to borrow some ideas from this one-time pad, but this time to use a more convenient short key. And then when we started looking at the stream ciphers, we saw that at the heart of the stream cipher, there is one component called the key stream generator. And this key stream generator is nothing but the random number generators. Now, random number generators, they could be done by software or by hardware. One way to do them by hardware is using linear feedback registers. And the reason why we're covering this linear feedback registers is because it is used by the A5/1 cipher. And there is another cipher. One of the first one, this one is implemented in hardware. The other one is implemented in software. So you get 2 flavors of this very widely used ciphers. So the material we already discussed, I will go through it very super quickly, just as a reminder, and then I dive deeper into aspects that we didn't finish last time. So first of all, the stream cipher is part of the family of symmetric key cryptography, which means we use the same key on both sides. And remember, this diagram is very important. It's a mind map to help us travel through this cryptography journey. And so far we are here. Next time, inshallah, we will start in the block ciphers. So it's all started with this one-time pad, and the idea of the one-time pad also in the digital world, you make your plain text as binary, and your key is also binary, and you encrypt using XOR and you decrypt using XOR. We already seen this and we already discussed it, but it is not practical, and the solution to kind of make it more practical is to go for stream ciphers. And instead of having a key that is the length of the plain text, you have a small key, and then you use the key generator to generate as many bits as you need to match the length of the plain text. So it kind of makes the one-time pad more practical, of course less secure, but more practical. You know, there is a trade-off here. If you want fully secure, it's not efficient and it's inconvenient to manage these huge keys. But if you want more convenience, you will lose. It's not 100% secure, but secure enough for most applications. And then we started looking into stream ciphers, and I discussed the difference between stream ciphers where we encrypt 1 bit at a time, and block ciphers where we encrypt 1 block of bits at a time, like 64 bits or 128 bits. We've seen all of this. The most important diagram of of the whole session is this one. It captures nicely the whole idea. So you have some bits that the message that you want to encrypt is made up of bits. And then what you do is you take your key, you give it as an input to the key stream generator. It will start generating key, basically key stream. And this key stream at the end of the day will be the same length as the message. But you, bit by bit, you do it bit by bit. And then you take one bit from the message you want to encrypt, one bit from the stream side, from the key stream generator. You do an XOR, and you send it to the other side. The other side will do the same. It will use, of course, the same key because it's symmetric cryptography, and it uses the same key stream algorithm. Must be the same key stream algorithm, otherwise it will not work. And luckily, it will do the same simple operation XOR to decrypt. So this is what we all seen. And then when we look at this component, this key stream generator component is the heart of the whole stream cipher idea. And at the heart, or the implementation, the actual implementation of the key stream generator is nothing but a random number generator. And that's where we started looking into random number generators, and we distinguished between these three types, and we saw where each one is, where we use each one. So for example, this true random generator, it's very useful when we want to generate a key, or we want to generate what is known as a nonce, something you use once. But we saw that it is not suitable for stream ciphers, because it is unpredictable and you cannot reproduce it. And in the stream cipher, you have to be able to reproduce the key streams on both sides. Otherwise, you cannot decrypt. There are many algorithms out there in math to generate numbers, to generate random numbers. And we looked at them, we will review some of them. They are very good, not bad. They generate a good quality random numbers, but they are not purely kind of independent. The next number depends on the previous number. So it's not purely independent. Plus, at certain time, it repeats. The cycle repeats. I will show you what this means shortly. So they are not bad, but we need something better. And they can also be cracked, because there is dependency between two subsequent consecutive numbers. There is some dependency. It can be somewhat cracked. That's why we need more sophisticated pseudo-random number generators that are harder to crack. Also, we go back again to the mathematicians, but we go for much smarter mathematicians to give us a non-breakable random number generators. So that's how it looks like so far. Okay, so let us now focus on this pseudo-random number generators. So, no, first, this is true random generators. I already explained them. They are statistically, they are very good statistical properties in the sense that they are unpredictable and unreproducible. They are very good for this, as I explained, for these use cases. If you want to generate a key or an ounce or a one-time pad, the true random number generators are excellent. And the way they work, you need to use some kind of physical process that has a random property. And I explained to you this before. And you use that as an input, such as listening to voices in your surrounding, or you use the heat or some kind of physical process, even in the components inside your, let's say, your computer, and you use it as an input and you convert it to a digital form. And that, basically the source will give you random numbers at the end of the day. You get random numbers, true random numbers. True random numbers in our case, because in the digital world we have zeros and ones, it means whenever you generate a number, one bit, the 0 and the 1 has equal probability, 50% each. But this is a pure random number generators. Okay, now, but of course they are not efficient, they are not as fast. while the pseudo number generators, you can generate millions and millions in very efficient, very scalable, and very convenient, of course. Okay, now, and then we started discussing in practice how people generate keys. And I explained that these are tools such as OpenSSL to generate keys. And I explained, although we will see this in more details, I explained just generating a key that will be shared by two parties in case of symmetric cryptography, or generating private and public key in the case of asymmetric cryptography. Now, pseudo number generators, typically the way they work, there is an algorithm. It's an algorithm. Typically, it takes a seed, and then it uses this, like, it takes a seed and it is recursive. You generate one number, and you feed it back to generate the next number. So already, independence is questionable, starting to be questionable, because like these numbers feed back to the generator to generate the next number. One of the most widely used pseudo number generator is the linear congruential generator. It's called LCG generator. It's a very simple algorithm. All it does, you need to have a seed, which is a number, a random number. Now the seed, if you are not doing stream ciphers, the seed could be a true random number generator. Yeah? But in our case, it's different. In our case, we want to use this algorithm for stream ciphers. So we really need, in our case, for it to work, we really need to be a perfect random number generator for stream ciphers. We still want it to be unpredictable, but we want it to be reproducible. Unpredictable means if I know a sequence, it's very hard for me to predict the next one. This is a good property. But at the same time, I want the sequence, the stream of bits, to be reproduced on the recipient side, for them to be able to decrypt. Yeah. So the way it works, you start with the seed, and then to generate the next number, all you do is take your seed, or because this is more general, take the previous value, multiply it by some constant, add another constant, and do yet another constant, mod n. So you take your previous generated random number, multiply it by a plus b mod m. Yeah. Now, where is the secret? What are the unknown in here? We have the a, the seed, the b, and the m. Although m is typically made public, like maybe 2 to the power of 31, some big number. So usually you have this unknown, the seed, the a, the b, seed, the a, and the b, yes? Now, how do we initialize this? When we first start generating random numbers, how should we initialize this? In the context of stream ciphers, how do we initialize these variables? Using the key. You know, the key is something shared between the two parties. Somehow we use the key to initialize those. But I'm sure you have used a random function, let's say in C or C++. How did you initialize the seed?
We give
From the time, if you remember. You use the time, because every time you run it, the time will be different, and hopefully every time you run it, you get a different random numbers. Why you get different random numbers? Because time keeps changing. Okay. Now, I just wanted to show you in C, in standard C, this is how they implement this algorithm in C. So you can see here the seed is hard-coded and these values are known. You can go to Wikipedia, you can find them. Of course, this will not help us. In our case, how do we initialize these values? Using the key. Yeah? And that's basically the trick. If somebody knows our key, they can plug them into the LCG and they can generate the key stream. So that is the whole idea. It's a known algorithm. Everybody knows this simple algorithm is used everywhere. Almost all programming languages have this built in. But they have maybe hard-coded values for the A and B and M. But in our case, for the stream ciphers, we cannot use, of course, hard-coded. If it's hard-coded, it's not useful. We use the key that is shared between the two parties to initialize the unknown, the C's, the A and the B. And maybe M is already, we agree on it, 2 to the power of 31, for example. So it is efficient, it is very practical, but it doesn't have all the cryptographic properties. It can be easily broken. Again, we go to the math to break it. So we use math to help us have a good random number generators, and use math again to break this random number generator. And the way all the attacker needs to have, they only need to have basically three sequences. If they manage to get three consecutive three consecutive numbers from your sequence, if they manage to have three consecutive numbers of your sequence somehow, that's a challenge, of course. If they manage to have these three, all they do, you know, the way you can write S2 is basically A times S1 plus B modulus M, yes? S3 is the same, A times the previous value, which is S2, plus B modulus M, okay? So the unknown here is become A and B. M is known. The unknown is A and B. This is a system of linear equations. And if you use your linear equation, your linear textbook or Wikipedia, you will find this formula. Because all these are known, you plug the numbers, you get A and B. And that's it. You have cracked the stream cipher. You can now predict the next number. Yeah? So it can be broken, although it's hard to basically get this S1 and S2 and S3, but suppose somehow you got it, then you can break it. So cryptographically, it's not perfect. It is breakable. That's why we need something much stronger, which is cryptographically secure pseudorandom number generator. That is really unpredictable. You cannot break it. You cannot, even if you have some values of the sequence, you cannot predict the next one. And here, there are many other more advanced algorithms, such as this blah. Those are usually the inventors, the first name of these inventors. They put as the name of the algorithm. And there are many others. You can have a look at Wikipedia. Here, the idea here, we understand the concept. We take some simple examples of the kind of implementation algorithm for us to really understand what's going on. But for more advanced algorithms, just be aware of them. We cannot go deeper into them. So far, I hope you got the idea of stream ciphers, that we need a key stream generator. And hopefully it is now clear this key stream generator is nothing but a random number generator. And this random number generator could be implemented either in software, such as implementing a linear congruential generator, LCG generator, or implementing a more advanced algorithm such as these. But you can also have a random number generator using hardware. This is just to keep our CE friends happy. They have something to do. We don't just monopolize the whole space and program in everything. We leave some work for them to do. This is where this linear feedback shift registers come in. These are hardware circuits you put together in some kind of architecture to basically help you to pump out random numbers, random bits, zeros and ones in a random way. So our CE friends, they are familiar with this more than us. But the basic idea is, first of all, we need to understand what every keyword here means. So we have these registers, which are nothing but they call them this scary name, flip-flop, some place to store 1 bit, okay? And basically, what we do in this case to be able to build this random number generator, we need multiple of these flip-flops, okay? And then what we do is we go ahead and initialize them. We put some values in them. How do we initialize those? How do we initialize these bits? Using the key. Whenever you need to do some initialization of, let's say, random number generator, whether it's in hardware or software, you use the key to do so. So you use the key and you initialize somehow your random number generator. So for us, our friends, CE friends, they see this as flip-flops, too hard for us. You can see them as kind of an array of bits. Every element of the array is a bit. It could be 0 or 1. Yeah. Now, of course, these are somewhat connected. And then you see this keyword here. I will explain the shift shortly, but let's first see this feedback. What this feedback means? Yeah. So somehow some of this flip-flop, the values here, we read them, let's say, not necessarily consecutive. We read, let's say, 2 bits, and then we take this and we feed it back to these registers. So it's kind of, imagine it as an array of registers. It has zeros and ones, and then every clock cycle, I will leave this one for our CE friend to explain. So this is every clock cycle. What we do, we go through, take the bits in these registers, and then what we do with them, we do an XOR, and then before we do this, every clock cycle we shift. What do we mean here by shift? Yeah, we take these values and we shift them to the right. For us to pump out one bit, because you know the purpose of this registers. The purpose of them is to produce each cycle to produce 1 bit, a random. So what we do is we shift all by 1 bit to the right. So this one will become kind of empty, sort of. Okay. So how we need to fill it? So how do we fill the bit on the left? We do an XOR on, let's say, on these 2 items, and then we do the XOR and put the value in there. And then this will continue over and over and over, generating random numbers. Okay, so this is how it looks like. And basically, you can generate, before you repeat, you can generate unique numbers 2 to the power of m minus 1. 2 to the power of m minus 1. This is how many bits you can generate. Minus 1, because if you initialize it, you should never initialize it with 0. If you initialize it with 0, it will stay in 0 forever. It has to be initialized with something other than 0. So 0 should never be there. That's why it's minus 1. Anyway, this proved to be very useful, but it can be easily broken. That's why in practice, our CE friends, they need to use multiple of those to make it unbreakable. So this is the concept. Is the concept clear? For us, let's just abstract it very abstract it to an array. Let's not use these scary flip-flop things. Just imagine it as an array of bits. We initialize it using the key, and then each cycle we push the elements to the right, and then we compute a new element based on a couple of bits that we decide. Okay, in this case, which bit are we using? Bit in position 1 and the bit in position 5. 1, 2, 3, 4, 5. In position 5. So, for example, once we push everything, 0 will come out, and this will be our bit, our random bit. And then 1 will move here, 1 will be moving here, 1 will move here, 0 will move here. okay? And then we compute. After we do the shift, we compute. So this one will be, after we do the shift, this will be 1, yes? And after the shift, this will be 0. So 0 XOR 1 is 1. So we place 1 there. And every clock cycle will do the same. So every clock cycle, we have 1 new bit, randomly generated. Now, this is very widely used, or this is the way this is the most widely used crypto system out there in the real world. Every one of us, maybe 80% of the planet uses this cipher because it's using GSM. So when, as I explained before, whenever you make a phone conversation or phone call, all the communication is encrypted between the phone and the tower. So, and it is using this algorithm, or using this cipher. It's called A5/1 cipher. I'm not sure why they named it this way, but in terms of implementation, this is how it is implemented. So instead of having one feedback register, you have 3. They work the same way as I explained, but the way it works, you have 3 registers, X, Y, and Z. Yes? Then what you do, you initialize them. Based on the cipher, this is the size of each one. So those of you who, our CE friend, who want to implement this, they need to go to Wikipedia or a book or whatever, the standard, and follow the exact design. How many registers they will have, how many flip-flops in each register. So register 1, 19 bits. Register X1, 19 bits, Y is 22 bits, and Z is 23 bits. The total, I think, 64 bits. Yep. And basically, in hardware, you kind of implement them this way, and then what will happen is remember, there is a feedback. Every register will have a feedback loop. So the first register, you cannot just pick any bits. If you want to implement this algorithm, for X register, which bit you should use to do the feedback? Yes, bit 13, 16, 17, and 18. Every cycle, you do XOR and you feedback the value to the leftmost bit, and you shift first, then you do the feedback. And you do the same for the Y, but this time for Y, which bits you use? 21, 20, and 21. And for register Z, which ones you do? 7, 20, 21, and 22. Okay? Now, not every cycle, not every clock cycle you shift all the registers. This is the trick. What you do is, there is something called, I think it's easier to explain here. There is something called majority. What you do every cycle, every clock cycle, you go to these bits. Can you see these bits? X8, like basically bit 8 in register X, bit 10 in register Y, and bit 10 in register Z. Yes? You take the values of these registers. Let's say the value of this one, let's say the value here is 1, the value here is 0, the value here is 1. So how many I have here? 1, 0, and 1. You do majority. Which one appearing the most? 1. So the registers where this bit is equal to the majority are the one you should shift. The registers that do not match the majority, you don't shift them. You know, here you do this trick to be able to do some kind of randomness. Otherwise, if you shift them all at the same, all the time, it kind of becomes kind of predictable. So all this magic is to make, at the end, pump out random numbers that are very hard to break and very hard to predict. You don't know. Next time you will get 0 or 1. It's really hard because of this architecture. So just to summarize, you have 3 registers, and these registers, you have to shift them, not all of them, you shift them based on majority. You look up values of certain bits, and you do the majority, you work out the value that is repeated the most. The registers where the bit is equal to the value that is the majority, you shift them. The others, you leave them as they are. So after you shift them, how you will generate the random number? You get the rightmost. You get the rightmost, and you do an XOR, and that's your digit. Okay? So you will think, in software, this will be so inefficient, but in hardware, it's super fast. That's where hardware implementation is very, very, very efficient. Yes, please. Yeah.
We only shift when the majority is 1?
Yes. No. Okay. You shift registers that have the value equal to the majority bit.
You shift when you say register, you mean flip-flop, right?
Sorry?
When you say register, you mean flip-flop.
I mean the whole register. I mean the whole register. Shift means move this one. The whole thing. Yes. Shift the whole register.
Oh.
Yes.
When what exactly?
Yeah. Let's do this example together. So basically, you watch these every clock cycle. You watch these bits: X8, Y8, Y10, and Z10. So this is my X8, Y10, and Z10. Every clock cycle, you extract the values of these bits. Now, what are the values of these bits? 1, 0, and 1. We do majority here as a function. This majority the result will be 1. So the registers where the shift, we call it shift bit, whatever they call it technically, where this bit is equal to the majority value, those registers will be the lucky registers that will be shifted. So will this X register be shifted? Yes, because the value in this bit equals to this majority value. Now, will this register be shifted? No, it will remain as it is. Next cycle, hopefully, it will be shifted. Okay, now this one, will it be shifted? Yes. So what we mean by shifting? So the 1 will become 0. 0 will become 1. 1 will become 0. And you keep doing this. Yeah? So this one will become what? 0. And this will become 1. Now, this value, you kind of have no value. You will override it. How you will override it? You go to this bit according to the algorithm. It tells you which bit you should XOR. You go to this bit, you do XOR, you get the result, and what do you do with the result? You feed it back. That's why it's called feedback register. You feed it back to the leftmost. And you do this. Will we be shifting Y? No. We will be shifting Z? Yes, the same trick. Now, after we do the shifting, what will be the value of 0? What will be the value of X? The rightmost bit, 0. This one, the rightmost bit, 1, because we didn't shift it. This one will shift it. So what's the value of the rightmost? 0. What will be the random value that we will pump out? Is 0 XOR 1 is 1. 1 XOR 0, 1. So we will pump out 1. Yes? Next cycle, what will be the majority when we evaluate the majority function? What's the value of X? X8, 0. What's the value of Y? 0. What's the value of Z? Because we shifted, remember? 1. So what is the majority value? 0. So which lucky registers will be shifting? This one we will be shifting, this one we will be shifting, this one we will not shift. So every time, this is how randomness gets manifested here. By doing this trick of majority, only you do majority, you evaluate the majority function, and only the registers where the shifting bit is equal to the majority value, those are the ones that will be shifted. Others will remain as they are. And you keep doing this to generate as many millions or billions of random bits as you wish. Very simple and can be built, our Cipher. And I don't know how to do this, but I'm sure our Cipher, and maybe, I'm not sure. Is this hard to build? I'm not sure. Hard or easy? Not that hard, yes? Feasible with what you have studied. Yeah. Okay, so, but our C aspirant, you don't need to be sad. There is also other string ciphers that are very easy to build in software. So we have now our CE people are happy. They know what to do to generate numbers. Now let's do in software. In software there is this RC4. I will do it very quickly. Please give me 2-3 minutes. Maybe next time I can. Maybe if it's not clear, I can go through it again. But very quick, what this RC4 stands for. First of all, it is invented by this reversed, I think, hopefully I pronounce it correctly. This is a famous guy in cryptography. He's still American, he's still maybe 70 years old, still around. It was invented in 1987. And the way it works is super simple, but very, very effective. All you do is, let me explain it through this. All you do, you take an array. You take an array that has 256 elements. Why 256? Because basically, a byte, how many bits we have in a byte? 8. And how many combinations of values you can get? 2 to the power of 8. 2 to the power of 8 is 256. That's why those are the possible values of the bytes. So what you do, the possible values is from 0 to 255, yes? From 0 to 255. All you do, you take an array, you initialize it with 0 to 255, and then you do permutation. You know what's permutation?
Switching.
Rearranging, yes, switching places. How you do this permutation? It is random, but based on the key. You do the permutation randomly based on the key. The way you do it, the way you do this permutation is very, very easy. So this is this first loop. All it's doing is just initializing this lookup table with numbers from 0 to 2, from 0 to 255. Yes. What the second loop is doing, it's iterating through this array of 256 elements, and it's computing this J index. So J is equal the previous value of J plus the value of the element I. The value of element I, the first time will be 0, 1, 2, 3, and so on, plus you also take the key. You remember the key? You take the key, and this is, of course, a naive implementation. You take the key and you create an array. And you start duplicating the key many times to match the length, or to match 255. Similar to what we did in Vigenère Cipher, if you remember. We take the key and we keep repeating it until we fill up an array of 256 elements. Yes? Then, so basically now we have two arrays. One has numbers from 0 to 255, and another array have values based on the key. And these values will repeat. If the key is 64 bits, I'll basically 64, yes. Yes, I will repeat it, let's say 4 times to fill up the array. Then I have two arrays, the same size. And I'll do this very simple loop to shuffle and to permutate this S. So initially, what's the values of the S array? 0, 1, 2, 3, 4, 5. After we do the permutation, randomly they will shuffle around. Maybe the first element will become 110. Second will become 200. We never know. It's all based on The permutation will be based on the key. So the way you do it, you take j, which is 0 in this case, plus the first iteration will be 0, plus the value of the element I, plus the value of the key at element I. You do the sum of these, and then you do modulus 256. Why we do modulus 256?
So it will not exceed.
It will not exceed the length of the array. Then all we do, we swap. The element that was in J will go to I and vice versa. So we swap. And we keep doing this how many times? 256 times. After we do this, we get a random value, a random array. And then we use it to pump out random numbers. The way we do random numbers again, what we do, I do another loop, goes from 0 to 255. And then what I do is, I basically, within the key generation, I also swap this, I compute I and J, swap them first, and then do I plus J mod 256, and that will be my key. I think easiest next time, inshallah, I will show you. It's very simple Python implementation. We go through it.